In this clip, I will focus on special series, series that are alternating. What is special about those series is that they take a very special shape. So you have consecutive signs in the sequence of a minus sign and a plus sign and a minus sign and a plus sign, etc., times an, where an is just a positive, not a non-negative number. This holds for all n. So as an example, what we've seen before, we had the alternating series corresponding to an equals 1 over n. And we get the alternating series by putting minus 1 to the power n in front of an. Yeah, so then we get the series minus 1 plus a half minus 1/3 plus 1/4, etc. Another example is the following, where we just take an equals n equal to n plus 1. Then what we get as a series, we get the infinite sum would then read as minus 1 to the power n an equals 1 minus 2 plus 3 minus 4, etc. What we'll do in the subsequently is focus on convergence of the partial sums. So one may question if this sum here, listed here, is existing. What we can see is that this sum is not well defined, since if you look at the partial sums, it starts with a 1, then you get a minus 1, then you get a 1 again, then you get a minus 1, etc. So here we see something that does not exist. This is a diverging infinite sum. Here we have a converging one, and that's the main contribution of the alternating series theorem, which makes a statement about convergence of these type of sequences. So what does it say? We have the following theorem. Suppose an, and now we start with an index 0 just for convenience, to infinity. So we take a monotonically decreasing sequence, which is non-negative, and it goes down all the way to 0, meaning that we have a sequence an which goes down and it has a limit 0. Now, what does the theorem say? The alternating series theorem now says that the corresponding series, the alternating series that we can build up by just multiplying the consecutive terms an by minus 1 to the power n, which sees to it that we have a changing sign from minus to plus, from minus to plus, etc., that this series is convergent. So we can express the S infinity, this sequence of partial sums, has a sum as it is converging. Moreover, we have the very special property and very nice property that the following holds. So suppose S is the sum of the series, right? So the limit of the partial sums. Then what we have is that we know that the difference between S and the nth partial sum is no more than the consecutive term an plus 1. And that's a very nice property. Suppose we would know S99. And we would know that A100 is 1 over 1,000. Then we would immediately know that S99 is, as an approximation, close to S, closer to S than 1 over 1,000. Okay, so an application, direct application, is the following, that we can immediately tell that the series that we build up from an equals 1 over n is converging. right? Since a 1 over n is monotonically decreasing and it has a limit 0. So this series has a sum. The proof of the alternating series theorem goes as follows. First, we will show that the series is converging under the premise is that the underlying sequence is moving downwards, is monotonically decreasing with a limit 0. And secondly, we show that we can estimate the sum by the n plus a n plus 1, right? So the quality of Sn as approximate value for S has an accuracy of at least a n plus 1. Okay, the proof goes as follows. So first we construct two sequences, and one sequence relates to the two sequences of partial sums. One is referring to the sequences with even indexes, right? So Bn is the sequence of partial sums of S to n. So what is it like? So we start with S a0 minus 1 plus a2 minus a3, etc. until we add up a to n. And a to n, of course, comes with a positive sign, right? Since we have an alternating series where we have minus 1 to the power n and minus 1 to the power an even number comes with a plus. Cn is the sequence of partial sums with an odd index number. So this is a0 minus a1 plus a2, etc., etc. And we have a to n minus a to n plus 1, right? So there are some clear properties here. The relation between Cn and Bn, well, Cn is just Bn minus a to n plus 1. So Cn is smaller or equal than any of those Bn's, right? Also, we have that C0 is smaller equal than Bn for all n. Well, why is that? If we just group our terms as follows, Bn is a0 minus a1, which is a non-negative number, and a0 minus a1 is equal to C0, right? So then we keep adding up, we pair up those elements like this, a2 minus a3, we add up, and as a final thing we get a2n minus 2 minus a2n minus 1 plus a2n. And we see that so a0 minus a1 is c0, and any of those differences that are mentioned here is larger and equal than 0. A2 is larger than A3, so A2 minus A3 is larger than 0, and this follows from the fact that AN is monotonically decreasing, right? So Bn is C0 plus things that are all non-negative, which means that Bn is larger or equal than C0. Similarly, we can show that B0 is always larger than any of these partial sums Cn. And the way to see it is that B0 is just A0, right? So that's the first element. And then, just as we did before, we're going to pair up odd elements with a minus sign and even elements that come with a positive sign, right? So we do it like this, and we keep adding those terms up. And then as a final term, we get this one, a2n minus 1 plus a2n minus a2n plus 1. And we see that A0 is B0, and minus A1 plus A2 is, of course, smaller equal than 0, since A2 is a monotonically decreasing sequence. So all its terms are smaller equal than 0, which means that Cn is always smaller than B0. It's not very hard to conclude that Bn is a monotonically decreasing sequence, and that Cn is a monotonically increasing sequence, right? So, so what we have here is we may conclude that Cn is monotonically increasing, right? And Cn is a sequence bounded by B0. Bn is moving down, so it's a monotonically decreasing sequence, and Bn is a larger equal than C0. So this means that both Cn and Bn are bounded sequences and they are monotonic. Well, in a previous video we have shown the monotonic convergence theorem. And the monotonic convergence theorem says that any monotonic sequence that is bounded has a limit. So we know that the partial sums related to Cn, these are the partial sums of the series of the alternating series corresponding to odd indices, is converging. It exists, and also we know that B is the limit for n to infinity of Bn exists for the same reason. Yeah, the Bn are the partial sums with an even index, and we know that this sequence is bounded and monotonic, so it must converge. Okay, but now we can make a statement about the absolute difference between B and C, since we can calculate the difference. Yeah, so B is the limit of n to infinity of Bn. C is the limit for n to infinity of Cn. We can take out, following the limit rules, we can take out the limit, so we have the absolute value of the limit of Bn minus Cn. And we can say something about this difference Bn minus Cn, right? Since the difference between Bn and Cn is just one element, so it's the absolute value, the limit of n to infinity of a2n plus 1. They differ only one element, right? And what did we know? Do we know about the sequence an? Well, the sequence an has a limit 0. So in particular, a2n plus 1 goes to 0 when we let n go to infinity, right? So we now have that the B and C must be equal, right? Since we started off with B minus C, and B minus C absolute is 0, so B equals C. So we have that the limit of the partial sums with even index, yeah, that will be the sequence S2n, has the same limit as the odd ones, right? So the partial sums with the odd indexes, right? And this all should be B or C, right? So when the sequence when the indices, the elements with the indices that are even are closing in on B, and the same holds for the the sequence elements S2n plus 1, so the ones with the odd indices are also closing in on B. This means that the whole sequence closes in on B, right? So we have shown that the limit of Sn for n to infinity has a limit, and this is the limit B. Proof of the final part can be graphic. It has a graphic way of doing things. So here we see that here we have bk, Here we bk plus 1. So the b's are, as we've seen, they are monotonically decreasing and they have a limit s, right? So this is at height s. And if we look at the odd partial sums, the partial sums with the odd indices, that's our sequence C. And C is moving upwards, right? So it's monotonically increasing, and it also has a limit S, right? So what do we see? So if we are going from S2K, S2K to S2K plus 1, well, what happens is we subtract here a value from S2K plus 1, and this value is a K plus 1, right? So we see that and by going up from S2K plus 1 to S2K plus 2, we're going to add up something positive, right? And the positive element there is a 2K plus 1, right? You see that every time we make a jump, and this jump is getting smaller and smaller as n is a decreasing sequence. So now suppose we look at the difference of s with s2k, right? So we see that the difference between s2k and s is this part, and now we jump. So the jump is bigger than the difference of s2k and s, right? So we know that this holds. The absolute value of s minus s2k is smaller or equal than the size of the jump downwards, and that's a2k plus 1. Similarly, if we now look at s minus s2k plus 1, so the difference of s with a partial sum with an odd index here, then we see in the same way, we see that it's smaller equal than a2k plus 2. Right? So both, if we compare S with a partial sum with an even index, we see that the absolute value of the difference is smaller equal than the consecutive term in the sequence an. And we also see the same thing for odd indices, right? So the absolute value of s minus s2k plus 1 is smaller equal than a consecutive term in the sequence an, which is a2k plus 2. So summarizing, if we just look at the nth partial sum, which is either odd or even, then the absolute value of the difference of s minus Sn is smaller equal than the consecutive term in the sequence an. And this concludes the proof.